Welcome to our study session Saturday live stream. Today we will be going over resistors, capacitors, and inductors. So this series is to review everything that me and my cousin know about electrical engineering. We're starting off with the basics, resistor, capacitors, and inductors, and let's see how it goes. Let me add in my cousin. Say hello.
Hello, guys. Anyways, nobody watching. Let's go.
Okay, here we go. Let's go. Just talk about everything we know about electrical engineering, starting with
I don't know shit.
resistors,
I don't know what is resistor.
capacitors, and inductors. Very foundations of electrical engineering.
Question for Richard. Why you write all capital for resistor, capacitor, and but not inductor? You hate inductor?
Alright, let me change that. Okay. Today we'll talk about resistors. Oh, it's kind of small. Blow this up. Talk about the what is it? Equations. What else is important? Series and parallel combinations. And then some brain teasers. Okay, and then capacitors and inductors. You learn the same thing. What is it? Equations, series and parallel, combinations. We also need to know non-ideal versus ideal, practical applications, and I think that'll be good enough for today. Anything else, Ray? Anything you want to learn?
I don't know, man.
Okay, let's just start with this. Alright. Resist. Blow this up. Alright, so the resistor is drawn like so. This is a resistor symbol. It's denoted as R. And then the Europeans, they like to draw this box. And that is the European resistor symbol. From what I heard, they like to draw this box because it's more resemblance of impedance than this. This is like just strictly resistors. So resistors, they kind of impede the flow of current. So like beep, boop, beep, boop is I. Is yellow is I, current. And the most important equation is Ohm's law, which is V equals I times R. This is like the golden equation. So
Shit.
Also, another symbol instead of V, a lot of physicists likes to use E because this denotes the electrical potential. Electrical
Prepare
potential.
type. It's hard to read.
Alright, check this out. Zoop. Oops. Zoop. Ink to text. Psh. Bam! Alright, so...
Wait, is this how you did the interview?
No, I didn't do this. So, yeah, you could write E equals IR instead of V equals IR if you want to denote V as E. Alright, so now we got what is it and equations. What else? Series and parallel combinations. Actually, there's more equations. Another important equation is power. Let's get power. Power equals P. P equals V times I.
Why you bring this equation? There's no R.
Well, you could substitute V equals, so what is it, right?
I square R.
Yeah. I R times I. So then you get I squared R. Alright, what else? Oh, I need to show the units. So R is usually measured in ohms. Very, very important. I is in amps. Amps. And P is in watts. Okay. And then let's just get into now because it's pretty important to know what amps is. Amps are coulombs per second. And coulombs is the charge in an electron. So the amount of charge per second is amps. And then if you want to solve for watts, you gotta know I, V, or I and R to get watts, which is the power, amount of power that you consume per second. Alright, so good in density. Any questions, Ray? Anything you want to add? Okay, let's move on then. This is important because the next step is when you have multiple resistors lined up like this. This is denoted as series combination. Series combo. And then when you got parallel combo, when you get resistors that are configured like this. So let's get R1 and R2 labels here. This is R3 and R4. Alright, so this is equivalent to R1 plus R2. So you just basically add the two resistors, and then for this, it's R3 in parallel with R4, and you could do it in two ways. For what I like to do products over sums, so R3 times R4 over R3 plus R4. And then the other way to do it is 1 over R3 plus 1 over R4, and then take the inverse of that. That's also very, very, very key equations. Series. Parallel. Okay, now let's kind of take what we've learned so far and dive deeper into this. So if you have voltage at this node, you got current flowing through these resistors. But then what's neat is that at this point it's a smaller voltage because it forms a resistor divider. Current flows through these resistors. Current are equal on both R1 and R2, but then the voltage is different because, as we remember, voltage equation is I times R. At this point, it's going to equal to I E times R2. So that's the voltage at this point. Like, let's denote as V2. This is V1. And then the other way to find out what V2 is to form a resistor divider. So to do that is V2 equals to V1 times R2 over the series resistance equivalent. So let's, using this equation here, and substitute it there, and you get solve for V2. So that's the resistor divider. Solving for series. Alright, for parallel, it's kind of vice versa, like the voltage on R1 and R4 are the same, but then the current is going to split. It has two ways to flow, R3 and R4. So this is what they call a current divider. Current dividers are solved by REQ over R1. oops, not R1, R3. That would give you that would give you, let's put some numbers in and say this is 5K, and this is 10K. And I don't know on the top of my head what the REQ is, so I'm going to do the equation. Products over sums, 50 over 15K, and get 3.33. So the REQ is going to equal 3.33K, and R3 is 5K. So then we're going to get that which is 2/3 of the current through R3, and then this is going to get 1/3. So this is the current divided equation that you need to use. REQ over your resistor, so R3 to solve for I3, and then for R4 you got to do REQ over R4, which is going to be 3.333K over 10K, and that's going to get you 1/3 I. So conceptually, current wants to flow with the path of least resistance more. So 5K is less than 10K, and 5K is 2 times less than 10K. So you're expecting 2 times more current through R3 than the current through R4, which is what we're calculating. 1/3 I is on I4, and then 2/3 I is through I3. Alright, that's the parallel combo, and that's the series combo. What else? Brain tears. Alright, Ray, here's a question for you. From what we learned so far, I want you to solve for the REQ of this combination. Okay. Do you know what the REQ for this? You wanna try it?
You draw it difficult. If you draw another way, it's going to be easier.
Yeah, it's actually very.
This is a hard way. This is a confusing. This is a fucking interview question, man. This is a confusing way to draw the fucking resistor like this.
Well, this is just like the test. They give you
know,
level
like
1, level 1 and level 2 in terms of difficulty level, and then for the test they just.
This is why I wanna trick you. Like, it looks difficult. I have to draw it a different way. Come on. Where's my?
Alright. see if I can help you out. So,
What are you doing?
I'm coloring. So all of this is one node.
Yeah.
Yeah, and then all of this is another node.
How to change this back to the easiest way to see it's the point?
And let's make some labels.
point.
This is, let's say, node A, and this is node B. So let's take a look at one resistor.
A is
at a
connect
time.
to R1 and R3.
Yep. So let's have
A is
R1.
connect to R1 and R3. B is connect to R2 and R3. So B is connect to R2, and R3. Or you draw the object A and B.
Yeah, but there one end is A and the other end is B. Right?
Wait, what? R2 is, oh yeah, that's true. Yeah.
And then
So it's three parallel with three parallel together.
yeah, bingo.
Yeah. I remember the left one. It's tricky. Professor is always like to draw it like this way.
Yeah.
It's so confusing. Like what's going on?
Yep.
Yeah.
Super confusing.
The way to figure out how to draw it, like how to see the easy way.
Yeah.
It's the key point to solve the problem. It's not a hard problem.
It's just tricky.
It's tricky, yeah.
Yeah.
Tricky.
So yeah, we analyze.
But sometimes you imagine like if people want to draw this as their schematic, you know what I'm talking about, Richard, right? As a PCB board design.
Yeah, I guess.
I guess the left way
Okay.
it's more efficiency or the takes less space than the right one or not. It depends on what the board design. Yeah, but this question is always in a test.
For schematics, you usually want to do what's on the right because
Oh, really?
it's less confusing. You want people to understand your schematic.
Why you want people to understand your schematics? Your design the board.
Yeah, because people are gonna work with you and they want to
That's
understand it.
What if you put the left one? Your coworker is going to call you like, Richard, you have a problem.
Okay, well the left one is useful if you have switches. So you have.
Oh, I see what you're talking about. Yeah.
Yeah, so this one
That's true.
makes more sense to draw like this.
Mhm.
Then you could short out certain resistors. So if you turn on the switch on B, then you short out R2 and R3.
Yeah, that's true.
You short out R2, yeah, A, yeah. You disconnect the A from R2. So yeah, both ways have different purposes, but this way is most preferred. So yeah, it's good that you knew what to do. Alright, now since we have 3 resistors in parallel, then you can't do the products over sums, you have to do it.
Yeah, you have to do that.
linears.
Yeah. Wow, yeah. Wow. That's so bad. Shit, what is that?
That's
Just one
hard.
over it. It's easier to draw.
-1. Boom.
Alright.
Good, nice. I think we killed the resistor section. I hope.
And Google, right now, just Google. even harder. It's like it's like 15 resistors with the left one. I don't have to solve it in 15 minutes in the interview.
Oh yeah.
The guy is just going to kill you. Like we have this high bars job for you.
Fine,
You have to
you're
solve
right.
this resistor values of equivalent resistor values in 15 minutes. I have like 50 resistors. Can you see what I want to test you? That's good. What the?
Yeah, I think there's 2 more funny resistor combinations.
Yeah, that's pretty of it. You Google it.
Yeah, but it's out of the scope of today's conversation.
Next time when the interview problems comes, we're gonna have to deal with the hardest interview you can ever see. Because it's frustrating interview questions for resistors, just resistor. It's going to be like, why do I have to do this, man? I'm the electrical engineer. I'm still do salesman. Why do I have to look at my coworkers' resistors and fucking confused the whole time?
Yeah, well, this one's actually pretty important, but I'll just tease it for next time. So
next time the Garage Factory SD hire question. Never going to hire anyone until the...
So we got resistors connected like this.
Yeah.
And then a resistor connected like this.
Oh, this is normal.
So this is the delta, and that's the Y.
Yeah. Delta and Y. The 3-phase, the power, the 3-phase connections. Yeah, this is normal. Oh my gosh, my memory is back. Oh shit.
Yeah, but do you remember the equations?
I forget.
Yeah, me too.
I think it's something square root of 3/3 or square root of 3. Something like that.
I think you're solving for voltage or power. Like,
oh yeah, voltage. Yeah. Voltage. Resistor. Yeah, voltage and power. Yeah.
So,
Square root of 3 and square root of 3/3 for voltage or power. But I never solved resistor actually.
okay, so the delta configuration is also known as the pi network. So you could kind of split this end like that.
Yeah, at the ground, yeah.
And then this is also known as a T network.
Yeah.
So it looks like a T.
Yeah.
And we'll just go over this next time. Once I study up what this is.
No time next time.
Also aside, I draw my grounds like this, but there's also multiple other grounds. There's
we normally draw the ground like that.
ground like
I
a triangle.
I don't like a triangle ground.
And then there's
I don't like
this
triangle ground. I never see this actually.
This is a lot of people use for chassis ground.
What's chassis ground mean?
It's like you connect it to a big metal object.
Why do you do that?
It's like to absorb the electricity. Like if you connect the ground to your car metal, that's usually what this is denoted as, like earth ground or some giant absorber ground. And these are
yeah, triangle I see in the old book.
Digital grounds.
Oh, digital ground.
And then this one's like analog ground. But then what ground is, it's like not really a ground. This is the true ground. These two are actually return paths. Like they're just a connection path. Like a reference. But these are the three main symbols that I've been seeing for grounds. So just FYI. So I would think this is the closest thing we could get to a zero.
That's why they're all.
But then these are actually just return paths. And there's like a reference. Yeah. All right. Cool. So let's go to capacitors and inductors. I like capacitors and inductors more than resistors.
Yeah.
They're more interesting.
Capacitor is the question. It's most questions. Inductor is too deep. Capacitor is pretty interesting. If the interview asking you hard resistor question, it's trolling.
What? That's trolling?
Interview, yeah.
Yeah.
If the interview question asks you hard, like just draw some hard schematic resistor and ask you to solve the R equivalent.
Yeah, just 1 hour straight resistor equation question.
1 hour straight, solve this problem. Instead of just asking the capacitor knowledge of how to use capacitors, more relevant. They want to hire this guy.
All right. Well, capacitors.
If you want
and
to asking
inductors.
inductors questions, kind of harder than capacitor, in my opinion.
Well, it's good to know both. They're like complementary pairs. Capacitors, inductors, alpha, omega, cat,
No, stop,
dog.
Stop.
No, really. It's you once you like know a lot of capacitors, you could know a lot of about the inductors too. Let me show you. First, let me draw the symbol. So capacitors look like this. Inductors look like this. Let's go with let's go blue with capacitors and green with inductors. All right. I would say the most important equation is IC equals C dVc over dt. That's like the golden equation for capacitors. And then for inductors, it'll be VL equal to L di over dt. Oops, I didn't do yellow. So you can kind of see the resemblance, like it has a variable equals to the component to a derivative. In the capacitor case, it's IC equals C of the derivative of VC over dt, and then the inductor is kind of the flip of that, so it's V equals L over di dt. So, oops, was not not fair.
Okay. I know how much you love capacitor.
That's true.
Fine. Fine. You just passed the 2 weeks of capacitor worldwide trip.
All right. So we'll probably get to explain this equation later. Let's talk about the practicality of capacitors. So the concept is it's a AC short, so this is kind of the AC resemblance of the current. It just whoop passes through the two plates.
The sound is extra.
And then for DC current, it gets hit by this bar. Gets denied. Blop. So AC, which means alternating current. Short. And DC, direct current. Open. This is kind of a rule of thumb. It's like a hand wavy thing to know, because the actual reason for this is because C has impedance, so that's denoted as Z, and that is equal to 1 over j omega c, and omega is frequency.
2 pi f.
Yeah.
Omega is not frequency. It's 2 pi frequency.
Fine, you're right. So omega is radians per second.
Yeah.
And the 2 pi gets radians, and F gets that 1 over S, which is per second. So the F is the frequency of the signal, the AC. So as your AC signal goes really, really high, then this denominator goes really, really high, and then 1 over a really, really high denominator gets you 0, like very close to 0. So then the impedance equals to 0. So let me do this. So when with F goes too high, like infinity, then your impedance goes close to 0. And then to the other way, when your frequency is closer to 0, then your impedance goes really, really high. So this is like the reason why we say AC short, DC open, because DC is a frequency of 0, which is like a no changing current. So you get a super, super, super high impedance, which is open. And then when your frequency is super, super high, then your impedance is close, going very, very close to 0. Alright, let's talk about inductors. So the inductors are the flip of capacitors, so they're DC shorts and AC opens. 20, 22. Okay. So we got Z as impedance, and it's going to equal to J omega L. And then if we do the same analysis. Omega goes 2 pi f. As f goes
Wow,
to...
that F is so short.
Okay, I'll fix that for you. How's that? So f goes to 0, then
You just want to cut the bottom
impedance.
part become small richer. No matter how the thing you draw so long or so short, you just want to draw it lower, the bar.
It's just I'm getting used to this.
Yeah. Yeah, you see. No matter how long you draw the line, straight line, you just want to cut it.
Alright, well, for the inductor case, it's more straightforward. It's directly related. F, as it decreases, Z, the impedance decreases, and as the F increases, your impedance increases. Alright, so let's actually talk about what capacitors and inductors are. I don't think I really delved too deep into that. So capacitors, as the symbol denotes, they're two plates charged at different levels. So we have, let's say, a charge here. It is like different from here, like 1 and 2. So these two different charges has generates like a electric field. And the amount of capacitance is what is it? It's the permittivity times the area of the plates divided by the distance. Let me double check that.
In Google.
Okay, so
Your favorite capacitor is betraying you.
so what I just said was right, except I
Okay.
drew the permittivity symbol.
What does the N mean?
So yeah, permittivity is actually E. So
not E. It's
yeah, epsilon.
epsilon.
Yeah, epsilon. So permittivity is like the it's like the material characteristic, and A is the square area of the plates, and then as your distance increases, then your capacitance decreases. So as the distance of the plates are farther away, you get less capacitance, and then the distance of the plates that are close, you get really high capacitance. And then for inductors, they kind of are like this, like wires rounded up, usually around like a core, and
It's always around a core, or usually.
yeah, I mean,
I
I
never
don't
see
know.
inductor.
I don't really know too much about the core. Like could it be air too? And could you make an inductor just without a core? Or it has to be like iron or all those other core metals. But inductors, they are permeability. So I think that's what I was drawing. This U symbol, mu. Mu times the number of turns times area over length. I think it's n squared. So permeability, mu, N, the amount of turns their inductor have squared.
N or W? N?
This is N.
Oh.
N for number of turns squared. Area of the circle of the loop, and then L length. So
Yeah. Better write this L. If you write a capital L, it's confusing.
yeah. So if your length increases, then your coil kind of spreads out. You get less inductance, and then
Wait, the length is the wire length or the
it's like the coil length.
or the coil length? The coil length.
Yeah. Like when it starts winding for the turns. So this L length from here to here, that is what is solved for inductance, which is measured in henries, denoted as H. And capacitance is F farad. Named after Michael Faraday.
That's why your favorite.
What?
So F.
F. So F is farads, which if you look at this equation is going to be the amount of current per change of voltage. And then for AH henries, it's the amount of voltage per change of current. So if you put that in perspective, if I have a big change of voltage, then you're going to get very, very high peaks of current. Boom! It's like you're going to shoot up. And for this case, if you have
blow up the capacitor. Yeah, that's what I do. That's what I do in school.
If you have very big change in current for the inductors, you can get massive voltage spikes. But if you have like a massive capacitor, then
it's going to like fire the home. Yeah, like that.
Well, I mean, if you have a massive capacitor, the change of voltage, like if the change of current will be less because
yeah. But if you make a really high voltage change, it's going to be really dangerous.
Yeah.
Really dangerous. Like a grenade. It's like a grenade.
Let's actually rearrange that golden equation. So it's going to be C equals your IC divided by your change of voltage. So as your C increases and your IC is constant, then your delta V would be less. It's like the inverse relationship. And then for the inductor, it's going to be your VL over your delta I. So if you have a fixed voltage across the inductor and your inductor is large, like very big, then your change of current is going to be small. inverse relationship.
This is what they're using for power bank
Yeah, yeah.
to be safe.
Bunch of inductors, bunch of capacitors.
Yeah.
And they're gonna be bunch of big inductors and
A
big
big inductor. That's why I see when we see the Amazon, the Anki, they have a huge inductor.
Yeah.
It's huge compared to capacitor. It's a huge inductor.
Alright, but you don't have to have huge inductors. We could talk about series and parallel combinations. You have multiple inductors.
But that's going to cost more. What are you talking about?
No, some big components cost more than multiple small components. Yeah. The only thing you have
Depends.
to...
For what I understand, I feel like the small is might be harder to make. I don't know about inductor.
Yeah, I mean you have to look case by case, but
Yeah, I know.
it's not a rule that one
But the thing
is
is,
cheaper
Richard,
than...
if give you a design, you have a design, like you prefer to use one component or multiple components to get the same result.
You need...
do troubleshooting stuff, multiple components.
So you should use multiple components.
Why? What if you get it easy? You don't want to troubleshooting like multiple components. Just want to get rid of it, and one of them, if it's work,
because there's two big reasons. One reason is all of these components are non-ideal. So you can mitigate some of the parasitics by using multiple components. Like for capacitors, for instance, if these components are not ideal, they're going to have parasitic resistance and inductance. So from what we discussed before, if you have resistors in parallel, then they reduce an equivalent resistance.
And Richard,
so use multiple capacitors.
Yeah, you mentioned that like in real life, the components, like same components, never going to be the same.
Yeah, there's tolerances. So that's the second reason. Second reason is precision. Second reason is if you have like a very precise value, like a 737 microfarads that you need, you can't get that with a single component.
Oh, I see. You have to
like,
order it specific.
Like a 470 plus like a 300 to get like a 770. Yeah, and using standard values are easier to get precise tolerances. You can get like a good 5%, 1%, X5R ceramic capacitor. That's maybe 805 or 1206. Then say a specific value, like a single value. So those are like the two main reasons why you should use multiple components aside from cost. And
but I think it's going to, if you use multiple components, is that easy to control or hard to control, like the tolerance?
Well, I'm saying it's not always the best. There are trade-offs. So the trade-off for using multiple components is it'll take
and
more...
you know what, Richard? What? When we build prototype, it's easy for us to debug or to troubleshoot, right? But when the manufacture production happens, multiple components in using one board, like you cannot the what's that thing called, the risk of hitting some components has like bad, like what's that thing called, has higher tolerance. It's going to have a higher risk. It's going to hit that thing higher risk. You get what I'm talking about?
Not really. So you're saying single components are better or worse?
better. If single components, what if this like I produce 1,000 units, right? Then this factory tell me like from this 1,000 unit they have 1 to 3% of failures, right?
Okay.
Okay, so this is what so they have constant 1 to 3% of failures, and if we choose to use 3 components, and 3 of them has 1 to 3% of failures, that one product is going to hit 2 out of 3 components fails. That chance is
Okay.
higher than the just hit 1 to 3%, right?
Uh,
Am I right? Possibility?
well, if you have more components, then you would have less chances that all of them fail.
Oh, really? Wait.
Yeah, because then you have to take in, if you have 1 out of 3, let's make it easier, like 1/3 chance of failing, then it'd be 1/3 times 1/3 times 1/3. But then if you
Oh,
have like 10, then it'd be 1/3 times 1/3 10 times. So then that number is gonna be less.
That's true.
But then you kind of brought up a good point. So what most people do to figure out this kind of risk analysis is they use Monte Carlo analysis.
What's that? What is that?
Monte Carlo analysis is they put in a sample, so they simulate like 1,000,000 times, and the 1,000,000 times takes in a Gaussian distribution of the tolerance curve.
Okay.
So then it like randomly selects like different tolerances for all the components and runs it 1,000,000 times to see a distribution of expected failures that would fall out of like a pass fail criteria of
They know
design.
they will simulate it like they will based on the information from different part and simulate the already have the simulated result before to produce production it.
Yeah.
So they know how much unit will going to fail.
Yeah.
Anyways.
Well,
Then they
usually they adjust out of, so they adjust the certain components so they wouldn't get any failure.
Really?
Yeah.
Do that? Is there no failures?
Well, that's what you want to do before you make things in mass production. Is try to your best to simulate so that you won't get failures. But then you won't account for everything, so then you'll probably
I know. There's always failures because reality is always fucking smash your fucking face.
Yeah.
Smash your fucking face. Reality is always smash your fucking face.
Yeah.
There's too much stuff because you cannot simulate analog world.
Yeah.
Your digital stuff cannot simulate the full analog world. It's too much stuff to consider about.
Yeah.
You have to consider about the components' feelings, right? We're talking about. Sometimes they are not happy. Sometimes they're happy. All right, next topic.
Well, all right. Let's go over the series and parallel combos. For capacitors in series, it actually reduces the capacitance. So the CEQ is actually 1 over C1 plus 1 over C2. And take that 1 over that. And for the parallel case, you actually add the 2 capacitors together. So it's C3 plus C4.
Exactly the same as resistor.
No, it's opposite.
Oh, it's the opposite way. All right. I always say that, but I don't know that's the opposite.
Yeah. I know what you meant. So inductors you follow the same as resistors.
You didn't even draw 2 inductors. You're lazy.
Boom, 2 inductors.
Don't care about the inductor feelings. It's so long. You need 2.
Thanks for catching that. Anyways,
Professor, you need break.
Do you need a break?
No, it's okay.
So this in series, you add the inductors together, and then for the parallel, you do the 1/, ordeal. Boom. Cool. Alright, what else is there? Actually, there's a few more equations that's important. I'll drop one more, which is energy. Energy equation, which is the energy stored in a capacitor is 1/2 C times V squared, and energy for the inductor is 1/2 L I squared. So another.
Yeah, this is I never remember those two.
Oh, well, the thing is with inductors and capacitors, they're energy storage elements. Like when you charge the capacitor, it holds energy.
Yeah.
And same with inductors, it holds energy. So that's useful to know. And then if you want to solve for power, you just multiply.
That's R or P? Yeah.
You have to multiply the energy equation by your frequency. Same with the.
Yeah, this is used really. I didn't use those two, like power energies. The capacitor inductor in my school when I was in school.
Oh.
It's pretty rare to see those equations.
It's very important for efficiency calculations. When you like discharge and charge capacitors and inductors, you get power loss, and that's how you solve for the energy and loss through like capacitors and inductors when you're like switching it, like for FETs and stuff. Alright, now we need to talk about non-ideal. This is very, very important. Non-ideal. Non-ideal capacitors. Alright, so non-ideal capacitors, they are represented as this. A lot of people joke, they say when you buy a capacitor, they throw in free components. which is not really good.
Wait, I didn't get it.
Oh, just usually you don't want to deal with these extra components because they make
noises.
Difficult to figure out how to use it. So there's series resistance. There's.
But it's cheap, right?
Well, I mean, yeah, there's no ideal capacitors that you could ever buy.
Yeah.
All of these.
Only in simulation.
Yeah. So, there's equivalent series inductance. So this is called ESL. There's ESR, which is series resistance, and there's also a like a leakage resistance, which is in parallel with capacitor, and then this is your C. So you get all of this stuff with your capacitor in the real world, which messes a lot of these losses, a lot of the analysis up, because it's a lot more difficult to deal with.
Yeah, when you do actual when we do actual design, we have to consider about all those.
Yeah.
Yeah. When you just do assignment, they never give you this kind of stuff.
Alright. So let me just give ballpark numbers. RP, let's try to ignore this because RP are usually like super high, like in the mega ohms. So this is essentially like an open.
Yeah.
Almost. Barely get any like leakage current across the capacitors.
Mm.
And this RS is usually super small, like in the milliohms, like the 1-ish milliohms or less. But the ESL is the pain in the neck because from what we learned is equal to J omega L. And as your frequency increases, then this whole impedance increases.
Oh yeah.
And that kind of messes with the whole impedance of the capacitor, because now you have J omega L in series with O1 over J omega C. So what you'll find is, let's simplify it to be like a series LC circuit. And then these two like impedances at one point where the impedances are equal. So let's say the impedance, or they call it X reactance of your L equals to the reactance of your C. So that takes in omega L equals to 1 over omega C. There's one frequency in which the omegas will make the reactance equal. So that's what I set up here. So when you solve for omega, you're going to get omega squared LC equals 1. And then you're going to solve for omega. So then this is, I would say, another golden equation. Square root of this. Let me get more space.
What?
Oops. Sorry.
It's okay, you don't need to fix it.
What? I mean, this is square root. I was adding
Yeah,
square
I know.
root. So this is what they call the self-resonance frequency. I mean, radians per second. The self-resonant radians formula, and then you can solve for the frequency by dividing it by 2f. All right.
Yeah. This is more even familiar than W.
Yeah. So what you'll see in a impedance to frequency graph would be like this. So the capacitors is going to decrease the impedance until this point, which is the self-resonant frequency, and then your inductor is going to kick in. Bam! It's going to overtake the capacitor impedance. So your non-ideal shape of the capacitor is actually this, because you have to factor in this ESL, and then if you have ESR, then this doesn't go to 0. This goes like really, really low, but not to 0. So that's very, very important to know. It's like the self-resonance of a capacitor, and that goes into you know, what happens if you put multiple of these self-resonance in parallel. And like this is L1, C1, L2, C2. You can actually just take these parts and look at them separately. So let's say you get like a self-resonance frequency at like 10k hertz, and then this gives you a self-resonance frequency of 12k hertz. Then you could sum those together to be, and then another something like this. And this is 10, 12. But then this point is like a little bit lower than that point because this point is higher than that point, and then this is like the rough shape. So then a lot of circuit designers, they have to factor in these ESLs, plot a graph, get this impedance curve per frequency to filter out the regions of signals that you want to attenuate. Yeah, life is complicated. Real life is complicated.
Yeah, that's true. Quit.
Alright, I guess I should touch on non-ideal inductors. Non-ideal inductors.
We already talked about non-ideal.
What? I said non-ideal capacitor. So you get your series series resistor, they call it DCR, and you get your inductance, and then you get this big fat, not fat, but you get some capacitance like this across your inductor, and then like we discussed earlier, you want to focus on your L and C because this is usually small. It's not 0, but it's like 1. Actually, it's not that small. So these are actually considerable. Say like 5 milliohms ish. Maybe more. Maybe like 15 milliohms. But let's just ignore it for now. So you get this.
Even if it's non-ideal inductor, we just want to solve the problem. We are making it somehow ideal, motherfucker. We just
Well,
we don't want to deal with all those non-ideal fucking shit anymore. We just make life easier.
hey, I need to at least touch on the idea of parallel.
Yeah, that's what I'm talking about. We know that dream is always dream, but we have to fucking see some dreams to move on, man.
Yeah, instead of going from point A to point C, I need to go from point A to point B.
Yeah. Shit.
So then you get this parallel combo. And then the impedance, you get the you could also solve the point in which the reactance equals to each other, and then it would form like an open. So an open, it would be, let's do this, J omega L equals to 1 over J omega C. Then wait a second. 1 over J omega L. Oh yeah. But you get rid of it's not. Yeah, you set the reactance equal to each other. And then this would equal to an open circuit at one point. So it's and let me just do this then. So I'm gonna derive why it's open.
Wait, Richard, why I see a black screen for your stream?
What?
I see a full black screen for your streaming.
Oh shoot.
The whole time.
Since when?
I forget. What happened?
This is gonna be bad.
Oh shit! We just don't know what's going on.
No one's been telling me.
I didn't even check. I closed it.
Oh jeez. Man, I had such a good thing going on.
Check it. When it happened? Oh my god! It happened a long time ago. What did you press? Oh, from the ground. From the ground.
Oh man.
Oh my gosh! People just watching our back screen talking the whole time. Oh shit!
We're gonna have a podcast then. Imaginary. Yeah.
You can upload the scene, Richard.
What?
You can edit it.
Oh, I didn't record.
Oh, I didn't record I didn't record the Zoom meeting too.
Oh, I guess we have to scrap this one.
What?
Do it next time.
Yeah.
Ah, sigh. Anyways,
Somebody left your friend left something? Is it friend?
what? Any chat? No? Oh, inspiring. Keep it up. What?
Ooh.
I think it was a YouTube subscriber. Shout out to his royal self.
Damn, it's like Oh wait, let me see. Oh my god, we talk about for 40 minutes. 15 minutes of dark screen. Which button did you press?
I think I don't know. What did I press?
Did you fix it?
Oh, I mean, right now it should be fixed. Yeah.
Yeah, now it's fixed. Shit! See you next time. Bye bye.
What should I do? What should I do? What should I do?
Time to sleep.
Damn. Alright then, I'm gonna end the stream and then not publish this one. and do it all over again next time.
Okay.